So we're not doing the.
I forgot to introduce him,
Oh.
but this is talking about the Clapeyron equation. I forgot how to pronounce it. Pretty much, you know, when exam time comes around and you start stressing and you start getting sweaty, that's because pressure, temperature, they're related. So, we're going to talk about that.
My name is Al. I'm part of Group 1, and I'll be talking about the Clapeyron experiment. So first and foremost, when you're starting an experiment, you have to worry about safety. So you have to wear safety glasses to protect your eyes, and long pants and shoes to protect your lower body. And if you want to protect your upper body, such as your arms, you can wear long sleeve or jackets. And I put observation there because even though your other teammates are doing the experiment and putting their hands on the equipment, you have to watch for them, because if they're doing the experiment incorrectly, it can potentially harm them and harm you. And closely follow the instructions from the manual. So for the background, the Clapeyron equation represents the relationships of saturated pressure and temperature. The latent heat of vaporization is the amount of energy to change liquid to a gas. And ideal gas law. We will be using PV and RT, if you guys remember that from thermo. We will approximate the specific volume in the ideal gas law to get this equation, the Clapeyron equation, which H is the latent heat of vaporization, P is for pressure, saturated, T, temperature, and R is the ideal gas law constant. And for our objectives, we'll be calculating the latent heat of vaporization using the data we get from the experiment. So your temperature and your pressure. We will be performing 2 experiments, actually only one, because your TA will tell you which one to do. With boiling beads or without boiling beads. And we will be using the Clapeyron equation to determine the latent heat of vaporization. And after that, we'll be verifying our results to the steam table, so it should be similar to the steam tables. And next we have our apparatus. On the right side, left side, sorry, we have our computer and our beaker and a thermocouple, and the hot plate that will be on top of the table. And under the table we have our pumps, the reservoir, and we also have our vacuum valve, and number 5 will be our pressure gauge. And for our procedures, we will be creating a low pressure in the beaker. So the beaker is actually sealed to make that pressure. And next one, we have to turn on the hot plate on high. Next, we have to check the thermocouple so to not touch the beaker, because that will give us inaccurate data. And next, when the water is starting boiling, we start recording our data. And for 5, we will increase the pressure using the vacuum valve slowly. Slowly is in bold, because when you do it, when the water stops boiling, you have to start over from the number 1. And next, we have to compare our values, data, to the tables, the steam tables. And when the temperature, when the pressure before it reaches atmospheric pressure, we have to bleed the valve using number 6 to prevent any buildup pressure in the beaker. Next, after atmospheric pressure, we have to check our values of pressure and temperature, and it should be the boiling point of water, which is 100 degrees Celsius. And lastly, turn off the hot plate and follow the shutdown procedure in the manual. So for our predictions and uncertainties, we have a pressure and temperature relationship. So using the equations, the Clapeyron equation, we should be able to solve the pressure when we plug in temperature. We have the lane heat of vaporization. Using the equation again, we should be able to solve for that. Just plug it in our pressure and temperature. And steam tables, it should be our values that we get from the data. The experiment should be similar to the steam tables. And for our uncertainties, the ambient temperature and pressure that can have an effect to the experiment's accuracy. And leakage, I was talking about the seal on the beaker, so we have to worry about that for the pressure not to leave in the beaker. And lastly, we have human errors. Any question?
When the procedure says boiling, does that mean like a strong rolling boil or like barely boiling? Is there like a goal there?
When it's just starting boiling.
Just starting to boil?
Yeah.
What's the difference between like with the beads and without the beads?
So with boiling beads, it doesn't really have an effect. It just makes the experiment safe and smoothly. Make it smooth.
And how exactly does it do that? It produces bubbles or?
It has something to do with boiling. So.
Okay, that's fine. Any other questions? All right, well, let's give them a hand.
All right, my name is Patrick. I'm in group 2, presenting the bomb calorimeter experiment. Okay, so the introduction in theory, the bomb calorimeter was first invented for the use of testing the the heat released by combustion, which was they first did it when they're making the oxygen bomb for testing liquid and solid samples for the bomb. And today it's the standard of testing the heat of combustion for samples now. And in this lab, we are trying to discover the thermal capacitance or heat of combustion of the sample that we're going to put inside of the bomb calorimeter. And that sample is going to be 1 gram of benzoic acid, I believe is how you pronounce it. And so it also uses the first law of thermodynamics to do this, which is equal to Q, the heat of combustion, is equal to the mass times the specific heat times the change in temperature, or you can rearrange it right here. And so the thermal capacitance for the bomb calorimeter is the mass of it times its specific heat. And again, it can be rearranged here for the heat of combustion. And the experimental setup and apparatus consists of the igniter going into the bomb right here, which is the stainless steel bomb plugged into the laptop with the analog converter. And the bomb is inside of the water bucket. It's submerged as well. And there's a thermocouple inside of it to measure the temperature and a motor that stirs the water to circulate it. And the bomb specifically has more subcomponents, including the lid, the housing, and the locking ring. The lid has an inlet and relief valve with electrode terminal, and the crucible right here is where the fuel sample goes into, and the ignition wire connecting to it. So the actual procedure, the first thing we're going to do is assemble the bomb, so we're going to measure 10 centimeters of the ignition wire and put the fuel sample into the crucible, and then prepare the water. So we're going to fill the bucket with 2 kilograms of water, and start the DAC software on the computer, and then the bomb will be submerged into the water, and we will ignite the ignition wire and record our data. And then we're going to shut it down. We're going to turn the motor off that's stirring the water, depressurize the bomb, open it, measure how much unburned wire is left, and clean it up. And so some expected results. A prediction of what the thermal capacitance will be based on knowing the system consists of 2 kilograms of water and 3 kilograms of stainless steel, you can find the thermal capacitance of the calorimeter using the mass of, not the heat capacity of the water and the steel to get an average value of that, and predict that for 1 gram of the benzoic acid, which releases about 26 kilojoules per gram, because we're just using 1 gram, you can expect about a 17.4 degrees Celsius temperature increase from adding the sample. And some sources of error possibly. So it wasn't specifically mentioned what kind of steel it was, so I just used a common one, stainless steel 304, but it's not known exactly which one we're using in the lab. And that, because there's a little bit of a range between different stainless steels, what their heat capacity is. So if it's not 304, that can contribute to some error. And also for the 1 gram of benzoic acid, I don't know how exactly it's going to be measured, so it might not be exactly 1 gram, and because its thermal capacitance is pretty significant, 26.38 kilojoules per gram. If it's off, that might have a pretty big effect as well. And yeah, that's it.
Okay. So, does anybody have any questions? Get off.
So, you may not know the answer to this, but how dangerous is the bomb if it's not exploding in water?
I don't think it's dangerous. It's pretty well contained. The bomb it has a housing around it, and it's inside of water. So if there was no water, I mean, we're not going to find out what would happen. You can probably look it up and find that out, but I would think it's probably not insanely dangerous, but yeah, I can't tell you.
Any other questions?
So this is a sealed apparatus, right? It's completely sealed, you don't have any viewing windows or anything. So when you press the ignition button, how can you say that your sample has actually ignited inside?
From the computer software, we're going to receive the data as it's happening.
So what kind of data are you expecting to see there?
I'm not sure exactly what it's going to record, other than, I mean, we're going to record the temperature
You
of
have
the
a
water.
thermocouple in there, right? So what does the thermocouple record?
Yeah, the change in temperature.
Yeah, so you should see a significant rise in
Yeah.
temperature of the bomb explodes.
Yeah.
That's how you know it's ignited. If not, you have to do the entire experiment again. Okay.
And I have one final question. Do you have to assume, like, is the barrel being adiabatic or something? Is that something you're assuming as part of the experiment, or?
Maybe the lab manual, I don't think it specifies. I'm not sure.
All right. I'll give him my hand.